Ever wonder what makes a lemon so sour? Or why soap feels kind of slippery on your hands? Well, today we're going to dive into the chemistry behind all of that. And it all comes down to one simple, powerful number.
So is it some kind of magic? Nope, it's just really, really cool chemistry. And this simple question gets us right to the heart of what we're talking about today.
You see, the secret is this constant tug of war happening in pretty much any solution that has water in it. It's a battle between two tiny charged particles, hydrogen ions, which we call H+, and hydroxide ions, or OH-. And the balance between these two, that is what makes a lemon acidic and soap basic.
Okay, so how do we actually measure that balance? We can't see the ions. Scientists needed a way to put a number on it, and that's where pH comes in. It takes that invisible chemical dance and turns it into a number we can actually use and understand.
So what does pH actually stand for? Well, the P comes from a German word potens, which means power. So pH is literally the power of hydrogen. It's just a way to measure how concentrated those H+ ions are. Now there's a formula there, a negative logarithm, but don't get too hung up on the math. The big idea is that pH gives us a direct reading of how acidic something is.
And if there's a pH for the hydrogen side of things, it just makes sense that there's a flip side of the coin, right? And there is. Meet POH. It works the exact same way, but it measures the concentration of the hydroxide, or OH- ions. This gives us a handle on how basic, or alkaline, a solution is.
Okay, so we've got pH and we've got POH. And it turns out they fit together perfectly on this really simple, elegant scale that runs from 0 to 14. Honestly, the best way to think about it is like a ruler, but for acidity.
And smack dab in the middle of that ruler is the most important number of all, 7. A pH of 7 is perfectly neutral. It's our baseline. This is the pH of pure water, where that tug of war we talked about is a perfect tie, an equal balance of H+ and OH- ions.
Now this is where it gets really interesting, because we can place things from our everyday lives right on this scale. Way down here at the acidic end, with a low pH, you've got stuff like battery acid and lemon juice. And all the way up at the other end, the basic side, you'll find things like bleach and drain cleaner. And check this out. Our own blood is just a little bit basic, hanging out right around 7.4.
So if you remember one thing about the scale, let it be this. A low pH, anything under 7, means it's acidic, with more H+ ions. A high pH, anything over 7, means it's basic, with more OH- ions. It's really that simple, and the further you get from 7, the stronger it is.
But here's the kicker, and this is super important. The pH scale isn't like a regular ruler. It's logarithmic. That means something with a pH of 3 isn't just a little more acidic than something with a pH of 4, it's 10 times more acidic. And a pH of 2? That's 100 times more acidic than a pH of 4. This is a huge deal, and it's why even tiny changes in pH can have massive effects.
So you might be wondering, why 14? Why does the scale stop there? And why is 7 the neutral middle? Are those numbers just random? Nope, not at all. It's all because of a fundamental property of water itself. Let's pull back the curtain and see the secret that makes this whole thing work.
It's called the Ionic product of water, or just Kw for short. And what it means is that in water, if you multiply the concentration of H+ ions by the concentration of OH- ions, you always get the exact same number. It's a universal constant of nature. It never changes.
And there it is, that magic number. At room temperature, that constant is always 1.0 times 10 to the negative 14. This single, unchanging number is the bedrock of the entire pH scale. It's what governs that whole chemical dance we've been talking about.
So, what's the big payoff from all this? Well, because of that constant and the way the math works, it gives us this beautifully simple relationship. pH plus POH always equals 14. This is why the scale is so elegant. If you know the pH, you automatically know the POH. It all just fits.
Okay, so the pH scale is an amazing snapshot. But what if we want to watch the movie? What if we want to see the pH change live during a reaction? Well, that's where a lab technique called titration comes in. And the graphs it produces, they tell a really cool story. So in a nutshell, titration is a really careful process. You take an acid and you slowly, drop by drop, add a base to it while you track the pH. The whole goal is to find that exact moment of neutralization, which we call the equivalence point. All right, story number 1.
When you mix a strong acid with a strong base, you get this classic S-shaped curve. You can see the pH starts low, it stays pretty flat for a while, and then boom, it shoots straight up. And that vertical jump, the equivalence point, happens exactly at a neutral pH of 7.
But what happens if we change one of the characters? Story number 2, a strong acid with a weak base. The story changes. Look at the curve, it's different. And here's the crucial part. Notice where that big jump is. It's not at 7 anymore. The equivalence point is now down in the acidic region, below pH 7.
And you can probably guess what's next. Let's flip the script again. A weak acid with a strong base. Now we start at a slightly higher pH, and again, look where the middle of that jump lands. This time, it's squarely in the basic region, well above a pH of 7. Each combination really does tell its own unique story.
And for our last story, what happens when a weak acid meets a weak base? Well, it's a little less dramatic, right? There's no big, sharp vertical jump. It's just a more gradual change. And because of that, it's actually much harder to find the exact equivalence point, which is why you don't see this one used as often for precise lab work.
All right, let's just pull it all together really quick. We learned that pH is our go-to for measuring hydrogen ion concentration. We saw that the 0 to 14 scale isn't just a line, it's logarithmic, so small changes have big effects. The secret behind it all is water's constant, Kw, which gives us that perfect rule, pH plus pOH equals 14. And finally, we saw how titration curves let us visualize the story of these reactions as they happen.
So I want to leave you with this final thought. This whole system, it's not just for beakers in a lab. It governs our oceans, our soil, our blood. And we now know that a change of just 1 pH unit is a 10-fold shift in acidity. So the big question is, if the chemistry of water defines the scale for life itself, what happens when even small changes in pH start to ripple through entire ecosystems? Something to think about. Thanks for tuning in.